So I'm Pratik. Today I'm going to talk about instantly verifiable VRF. So I'm from Supra, and this is a joint work with the Supra research team, Jacob, Aniket, Pratyay, and also Lucian from CISPA, and Arvind from University of Sydney. So before going into instantly verifiable randomness, I'll talk about on-chain randomness. So we all know that on-chain randomness is useful. For example, you can play on-chain poker, on-chain lottery, and you can also mint NFTs in your favorite on-chain game. And recently, Chainlink showed that they fulfilled around 17 million randomness requests, and Supra DVRF also fulfills around 400,000 requests every 3 months. So there's a lot of demand for on-chain randomness in the randomness space. So now, coming to the natural question, how do we define good randomness that can be used on-chain? Firstly, the randomness should be unbiasable. That is, no one should be able to bias the random value. Secondly, it should be unpredictable. That is, no one should be able to predict what a future randomness value should be. Right? Otherwise, if you are playing on-chain lottery, then you will always buy the winning lottery ticket if you can predict the random value. And thirdly, we need public verifiability, where the on-chain randomness can be publicly verified that it was correctly generated. Now the question is, since everything happens on smart contracts in the blockchain space, how do smart contracts get good randomness? So the first approach that comes to mind is using a pseudo-random function or a primitive called PRF. So here, given a secret key SK, okay. So here, given a secret key SK, you run the function f on this input x to obtain the output y. And now PRF ensures that the output y is indistinguishable from a random string given sk is hidden. However, there's a problem over here. We all know that smart contracts cannot store secret keys, right? You cannot store private state on the smart contracts. So that essentially boils down to how to store the secret key securely. So the solution is to rely on off-chain computation. That is, rely on an off-chain company, for example, Chainlink or Supra, who will have their own secret key SK, who will store this SK off-chain, and then perform the PRF computation off-chain, and then produce a proof that the output is correctly computed. So let's see this in more details. So this primitive of PRF gets upgraded to VRF, verifiable random function, because now here, instead of just generating the output y by running the PRF, you also generate a proof pi that the computation was done correctly. Okay, so now this primitive of VRF satisfies these three properties that we need for on-chain randomness. Firstly, we need unbiasability, that is, the output y cannot be biased, so that is guaranteed. Secondly, the VRF security is similar to the PRF security, that is, if SK, the secret key, remains hidden, the one can predict what the output y will be on any given input x. And thirdly, we get public verifiability, where the key owner can produce a proof pi, which by verifying you can be ensured that y is indeed the computation on x using sk. So you will be ensured. So anyone can publicly verify on the blockchain. So now let us try to use this VRF primitive to generate on-chain randomness. So this is how a traditional randomness service looks like. So Supra Chainlink uses this framework. So here on the right-hand side, we have the VRF service. So the VRF service initially samples the VRF public key and the secret key. So this is very similar to a signing key, right? So VK is like the verification key and SK is like the signing key or secret key. So the verification key is posted on the blockchain. Anyone can access it. And now when a user wants to request randomness on an input X, so it forwards this randomness to the smart contract over here. And now the smart contract is going to format this input X into some format called INPs. Let's call it input. So you can consider INP as X comma some counter. Okay. And now this INP is forwarded to the VRF server or the VRF service, which computes the VRF to obtain the output Y and the proof pi. And this output y and proof pi is forwarded back to the smart contract. The smart contract verifies the proof, and uploads the proof on the, proof and the output on the blockchain so that anyone can view it and use it, and then forwards the output to the user. So this is how a traditional VRF service looks like. Now let's try to use this VRF service for a Web3 application. Let's try to use it to play a snake and ladder game. Okay. So in a snake and ladder game, we all know that you need randomness for each round. So each round needs a dice value, right? So you roll a die, and based on the die, you make your move. So if you want to use the VRF service to generate the die value, so you have the VRF service on the right. So the user is going to invoke the VRF service with the first input, say round one, and this input is going to be provided to the smart VRF service via the smart contract, and the VRF service generates the die and the proof that it was correctly computed. And this die and proof is sent back to the user. The user uses it and proceeds to the second round. And this will be repeated for, say, 48 rounds, because an average snake and ladder game requires 48 dice rolls. Okay, so if you use this traditional VRF service to play the snake and ladder game, where you want the die value of a particular round to be verified and used before starting the next round, then it would require like 48 queries to the VRF service. And this is going to be very expensive, because it requires like 48 queries to the VRF service. So that's gonna cost around $15 if I take the Chainlink gas cost estimates. So here, what do we want? We want that the user can generate the die value, right, and verify it, and then go to the next round and again generate another die value and verify it. But we don't want to query the VRF service multiple times. So we want to kind of amortize the cost, okay, of this. Yeah. So the problem over here is n different randomness requirements require n requests to the VRF service. So that brings us to the question that, can the user query the VRF server once and reuse the output? So in that way, the user will just query the VRF service once, just pay the gas cost once, and then reuse the same output to generate multiple outputs. Okay. So to partially answer this question, the Supra team had developed FlexiRand, or output private VRF. So this was accepted last year in CCS, but we didn't completely solve the problem. So let me talk about FlexiRand, and then I will go into the problems. So in FlexiRand, it is very similar to traditional VRF service that I described previously, except now here the user runs the entire protocol over a blinded version. So the user will query the VRF service on a blinded input, or like an encrypted input. And this blinded input is provided to the VRF service, and the VRF service gives you a blinded output and the blinded proof. So no one will know what is the value of the output and the proof, only the user will know it. And now this blinded output and the blinded proof is uploaded on the blockchain and provided back to the user. And now the user can unblind this Y whenever it wants to use it, and then unblind this Y and proof Y, and then use Y. So here, so the difference of this from the previous VRF protocol is, here the output remains private until the user wants to reveal it. So now, using this output private VRF, we can reuse or cost amortize the VRF query. So before the unblinding, so let me show you how you can generate multiple local random values which are verifiable. So what the user will do is, before unblinding, the user generates multiple random values z1 to zn using a hash function each. So what it will do is, it will generate z1 as hash of 1 comma y, hash of 2 comma y, dot 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 hash of n comma ny, right? So this is like, consider here n as 48, then these are all the die values. So to verify, and when the user wants to verify the z values, the user will just unblind y and pi and reveal it. And now anyone can verify that the z1 to zn are correct by verifying y and pi, and then recomputing this z1 to zn. So this is how you can cost amortize that one VRF query to generate n outputs. But there's a slight problem over here. The problem is, you cannot verify the z values independently. So what do I mean? So let's see. So to verify z1, you need to make the y and pi public, okay? And that would leak the later values like z2 to zn. So you cannot independently verify the z values. All the z values have to be verified together. So as a result, these z values are not instantly verifiable. So you cannot really use it in the dice game that I showed you previously, because you wanted to verify each of the die rolls separately, independently when they're used. So the question that we ask is, can we verify each zi value independently? Basically, can we verify zi without leaking zi plus 1 or any zj? So that brings us to the question of instant verifiability. So the question is, can we instantly verify extended outputs without leaking the other outputs? Okay. So basically, we want the user to query the VRF server once and then generate multiple outputs which can be independently verified and used in different applications. We don't want the user to query the VRF server multiple times for different applications. That will save up on the blockchain delay and also the client server latency. So before going into our result, let me compare with the existing literature. So the traditional VRF services do not allow you to reuse the output because the output over there is public, and you cannot also do instant verifiability, or the output is not instantly available. You need to go through two blockchain transactions, and the client has to make the query to the VRF service and so on. But it can be deployed on any blockchain because uh, it does not rely on the underlying blockchain consensus algorithm. FlexiRand, which I discussed previously, allows you to do like reuse the output. However, the output cannot be instantly verified, as I described. You need to verify all the outputs together. So it is not instantly verifiable. But again, you can deploy it on any blockchain. And there's a recent protocol by Aptos called Aptos Roll, which is their randomness service. So in this protocol, like clients or users submit a bunch of requests, and they first run a consensus on the requests and then perform the VRF computation on that block and then adds it to their blockchain. So their output cannot be reused because the output is public, but their protocol is very fast and it takes around 1 or 2 seconds. So their output is almost instantly available. However, their protocol cannot be deployed on any blockchain. You have to request randomness and use it on the Aptos role blockchain because it specifically relies on the Aptos, like mixing up the Aptos randomness generation with the consensus. And finally, we have InstaRand, where I will show you how to reuse the output, and the output is instantly verifiable. I mean, you can instantly generate multiple outputs without querying the VRF service. You can verify them, and you can deploy it on any blockchain because it does not rely on the underlying blockchain consensus mechanism. So now let me talk about InstaRand, or instantly verifiable on-chain randomness. So here are the properties of InstaRand. So we support pre-computation. So the user will perform like query the VRF server only once to generate a VRF output, and then in the online phase or in the separate phase, the user will reuse that single VRF output that it obtained from the VRF server to generate multiple different outputs. Okay, this is similar to FlexiRand. But each of these different outputs can be independently verified. So you can generate the second output first, use it, verify it, and later on you can generate the 100th output, use it, verify it, and so on. So this is where we improve our FlexiRand, and this is how we can, like how our InstaRand protocol can be useful in the dice roll game. And now the InstaRand protocol can be, I mean, the extended outputs can be used on any blockchain. So it does not rely on any blockchain property. So we just need a bulletin board. So yeah. And finally, InstaRand can also be used to upgrade existing randomness services like beacon services or VDF solutions to provide this output reusability and instant verifiability feature. So I will show that in the technical slide, in the next slide actually. So yeah. So InstaRand proceeds in two phases. One is the one-time pre-processing or pre-computation phase. Another is the online phase. So if you look at the pre-computation phase, this looks very similar to the traditional VRF service. On the right-hand side, we have a VRF service, right, which can be Supra or it can be Chainlink. So the VRF service samples its own VRF public key and secret key and posts this public key, which is VK, on the blockchain. And now there's a slight difference on the user side. So now the user will not query on input X, rather it first samples its own key pair for the VRF. So it samples a user public key and user secret key. So the idea of InstaRand is basically chaining a client side VRF with a server side VRF. Okay. So now this client side VRF public key is sent as input to the server side VRF. Okay. So here the client will query the server side VRF on input X comma UPK. And now this VRF service will compute the output Y on this INP, which is like a formatted version of XUPK. And then this is sent back to the smart contract, and this is sent back to the user. This is again similar to the previous randomness service protocol that we discussed. So this is how the pre-computation looks like. It's very simple. Just we replace the user side with UPK and USK. And now in the online phase, I will show you how the user will generate instantly verifiable outputs using this USK, user secret key, and this output Y. Okay, so this will happen in the online phase, and there will be no interaction with the VRF service. So before going into the online phase, let me tell you the difference that we need to make so that our InstaRand protocol can also be applied to existing beacons or VDF solutions. So we just need to replace this VRF service with any randomness beacon or a publicly verifiable randomness service like VDF service, which provides the same template, right? Or the same interface. You take in an input and you give an output along with a proof of correct computation. So if you provide the same interface, then InstaRand can be used to get output reusability and instant verifiability on top of that service. Okay, so now let me go into the online phase, how we instantly generate the outputs. So note that from the pre-computation phase, these are the values which are posted on the blockchain. So the verification key VK is the server's verification key, the Y is the output of the server, pi is the proof, X is the input, and UPK is the client's public key. So we mainly need this X, UPK, and Y. Okay. Now to generate, suppose we want to generate the first output, first extended output, the user will locally query the VRF, like locally run its own VRF algorithm using USK. So it generates W1 by computing the client side VRF on X, Y, and 1 to generate W1. And it also gets a proof that pi1 is correct. So this X, Y, and 1 is basically a nonce, right? And it computes the client side VRF to generate W1, and then it sets the first output Z1 is hash of 1 W1 X and Y. Okay, so it's basically the client side VRF evaluation on top of X, Y, and 1. And now the output Z1 and the proof is sent to the smart contract where it's going to be used. So in our example, this will be the dice roll smart contract. And now the smart contract can instantly verify the output by verifying the proof pi1, which will ensure the W1 is correctly generated. And now it recomputes Z1 to be ensured that Z1 is correct. And similarly, to generate the second output, the user can generate W2 by running, again, like computing the client side VRF on X, Y, and 2 using the user secret key. And it obtains the proof, and Z2 is similarly computed as hash of 2 W2 X and Y. And the output is provided as Z2 and the proof. And the smart contract will instantly verify the second output by verifying the proof pi2 and checks by recomputes Z2. And note that here verifying Z1 does not leak Z2. This is due to the VRF security of the client side because of the secrecy of USK. So this is what we are bringing something new to the table, right? So each of these Z values can be independently used and verified without querying the VRF service. Okay, this was not previously possible. So that's what we are bringing to the table. And now this is a informal security argument. So this is how our protocol looks like in 3 lines. So the VRF server computes the output Y by running the VRF protocol on X comma UPK using its own secret key SK. And then the user generates the ith extended output by locally evaluating the VRF on X, Y, and I using USK, and then running the hash and getting the output ZI. So now talking about the properties. First, the ZI value is unbiasable. This final output is unbiasable because Y will be unbiasable. So the moment the user posts UPK on the blockchain, and queries for randomness on it, uh, it becomes like everything becomes fixed. You cannot really bias it. So y is also kind of fixed given vk. So yeah. And now talking about unpredictability, wi and hence zi is unpredictable due to the security of usk. So no one can predict what is usk other than the client. So if the client is participating in some other application, it cannot predict some other client's instant and output. And finally, the main feature that we have is instant verifiability. Each ZI can be verified without leaking ZK. This is due to the public verifiability of VRFs. So now coming to the experimental evaluation. Uh, so as you can note that there are two VRF protocols, one on the server side and one on the client side. So we instantiate the server side VRF using the decentralized Glow VRF, and on the client side we deploy the DDH VRF or the Chainlink VRF. And our pre-computation phase requires a single query to the DVRF service, and that requires two on-chain transactions. So this is same as Glow DVRF of FlexiRand. And in the online phase, each client can generate instant outputs in less than zero point 0.2 milliseconds, and these can be verified in zero point 0.2 milliseconds as well. And finally, we do a gas cost comparison. So we generate n instantly verifiable outputs and compare FlexiRand, Glow DVRF, Chainlink VRF, and InstaRand over here. So InstaRand requires only n plus 2 transactions for n outputs. So we are in the one transaction model, whereas others are in the 2n transaction model. And that's why we start getting better numbers for over others when there are more number of outputs. So we are always better than FlexiRand and Glow DVRF, but we are initially worse than DDH VRF or Chainlink VRF because they don't rely on BLS. We have to perform one BLS verification. That's why we are more expensive. But gradually we become better for 7 outputs. So finally, to conclude, we introduce the notion of instantly verifiable random function, and we show constructions from plain VRF functions. We don't need any structure or any special new cryptographic primitive. Any VRF function suffices. And our protocol, InstaRand protocol, supports pre-computation, right? So you can run in the pre-computation phase. Make the client can make the query to the server in the pre-computation phase, and in the online phase, the client can instantly generate n outputs using n plus 2 transactions, where these two transactions are initially in the pre-computation phase. And also, we can upgrade existing services with instant verifiability with the ideas that I mentioned in the one-time computation pre-computation model slide. So, thank you. Yeah. Questions?
I have a question. So, in your final solution, the client can know. So, once given Y and it knows USK, it can know all the sequence randomness in one shot, right? Why is that okay? So there's no. So like for some games it might be okay, but some other games it may not be okay, right? To know the sequence of future randomness a priori.
Right. Yes, correct. So we have a protocol where you can also prevent this client pre-computation. So that is more complicated.
Okay, but you also support that
Yeah,
that even the client
and
cannot know all the future randomness.
yeah, the client cannot know all the future randomness values, but also even just given this protocol, where the client knows the future randomness value. So I have actually an application where, so suppose you run the same snake and ladder game where there are two incident clients, right? So here they can locally generate the two random values and they can combine them. So here there is no interaction with the VRF server. So even though I know my random value, you know your random value, but we can hash our random values together and then we can play the game. So in some applications it's more efficient than doing a generic two party. Doing a generic VRF solution.
Hi. Um, but why do you need this hashing on the user side? Why do you need the hashing on the user side? It's because I think that everything holds also if you just like keep this W as a randomness. So where does this hashing come from?
As in this ZI computation?
Yes.
Yeah, so there are, okay. So there are some VRF protocols for which, like, there are very artificial VRF protocols where you can break security. So something called biasable VRFs, and those are possible. So we have to capture them as well. Since we are proposing our solution based on plain VRF, we have to also consider the case that the client side key can be bad, and that can bias the randomness, final randomness. So that's why we need to include for unbiasability, we need to include the server side output as well. So I can take this offline.
Okay. Yeah. Thanks.
More complicated. Thank you.
Any more questions? We can take one last question. All right. I think thanks a lot for that informative session, Pratik.